You know that a balanced chemical reaction is a chemical reaction and a chemical equation in which there are exactly the same number of each type of atom on the left-hand side as on the right-hand side. Now let's look at a process for obtaining a balanced chemical equation from an unbalanced one. And the technique that I'm going to show you is called the method of balancing by inspection. Now, unfortunately, there are no hard and fast rules that explain to you how you get a balanced reaction by inspection. So the best that I can do is to show you how it works for several examples, and hopefully you'll get the idea. The first hint that I'm going to give you is to start on the molecule or compound that is the most atomically complex, meaning the one that has the greatest diversity of different types of atoms. So let's look at this first reaction. This is the reaction of calcium oxide plus carbon to form calcium carbide plus CO, carbon monoxide. And the point is, for this reaction, is that calcium carbide is a source of acetylene, and so people who are spelunkers, or people who go down into caves, used to at least take calcium carbide down, and that's how they lit their way. Now, when I talk about atomically complex, what I mean is different types of atoms. So here we have calcium oxide has 2, calcium carbide has 2, and carbon monoxide has 2. So in this particular one, it doesn't make a whole lot of difference where you start. You could start on any one of these. But the other side of that idea is to leave those pure elements that might appear in the chemical equation for last. So that means for sure we're not going to start on carbon. And the reason is that you can vary the amount of carbon in the balanced reaction without changing anything else, so it's really good as sort of the last thing to adjust. Think of it as adjusting this reaction. To get it balanced, you can adjust the amount of carbon without adjusting anything else because carbon appears as a pure element. Now, the second idea I want to convey to you is that you're not allowed to change these subscripts. In other words, this is calcium carbide, and that too says that it's calcium carbide, and you're not allowed to change it. Changing this too would be akin to having a recipe that calls for flour and changing it to chocolate. You're just not allowed to do that. You can change the amount of flour, but you're not allowed to change the type of ingredient. And if you change this too, you would be changing the type of ingredient. Okay, so let's give it a shot, get started on this problem, and see where it leads us. So since there's not really any difference between any of these three, let's go ahead and start over here. Actually, here's another idea. Typically, the first molecule or compound in a chemical reaction is the one that's the most interesting, meaning that's the thing that the chemistry is being done on. And so that's also another good place to start if you don't have any other guide. So let's start here, and let's put a 1. And what that immediately says is that there's only one calcium atom on the left-hand side of this balanced reaction. So that means that there can only be one calcium on the right-hand side, which means we necessarily immediately have to put a 1 right there. Because there's only one calcium here, there can only be one calcium here. Now, we're going to leave carbon for last, so let's do oxygen next. We have 1 times 1 is 1. So that means this coefficient, this stoichiometric coefficient, also has to be a 1, because 1 times 1 is 1. And now we can do carbon. We have a total of 1 times 2, or 2 carbons, plus 1 more carbon for a total of 3 carbons. And so that means this coefficient is a 3. And this now represents a balanced reaction. Let's look at this next example. This is a reaction of phosphorus pentachloride and water to form phosphoric acid and hydrochloric acid. And now it's a clear-cut example of one that has the greatest diversity of atoms. Phosphoric acid has 3 different kinds of atoms, and each of these others only has 2 kinds of atoms. So let's put a 1 here. And now, next priority would be, we have to fill in another number. Again, going to the beginning of the reaction is a good place to go. We can do phosphorus next. 1 times 1 is 1, so that means this coefficient. There's only 1 phosphorus in phosphorus pentachloride, so that can be a 1. Now we can do chlorine. There are 5 chlorines on the left-hand side, so that means this number has to be what? Has to be a 5. Okay. And now let's do hydrogen. There are 5 hydrogen atoms in hydrochloric acid, and this 5 hydrochloric acids, and there are 3 hydrogens in this phosphoric acid for a total of 8. There are 8. Then this number has to be a 4. This coefficient has to be a 4 because 4 times 2 is 8, and 3 plus 5 is 8. And now let's check the waters. We have 4 waters. Check the oxygens. We have 4 oxygens, and we have 4 oxygens. So this is a balanced reaction. And finally, let's look at the reaction of benzene and oxygen to form carbon dioxide and water. We're for sure going to leave oxygen for last, since benzene is the first element and everything else has, or first ingredient, and everything else has 2 different kinds of atoms. Let's put a 1 here. Balance for carbon means we put a 6 there. If we balance for hydrogen, put a 3 there, because 3 times 2 is 6. And now let's balance for oxygen. 6 times 2 is 12. 3 times 1 is 3. 12 plus 3 is 15. What number has to go here? Whatever it is, when we multiply it by 2, has to give us 15, which means that that coefficient is 15 halves. Now, by convention, we're going to express balanced reactions with whole number coefficients. So that means 15 halves doesn't cut it. All these other numbers are fine. These are all whole numbers, but 15 halves doesn't cut it. We need to multiply by a common factor all the way through, and we want to choose the smallest number, which clears the fractions, meaning in this case 2. And so we're going to express this correct balanced reaction as 2 molecules of benzene plus 15 molecules of oxygen goes to 12 molecules of carbon dioxide and 6 molecules of water. In other words, multiply each of these by 2. So 2, 15, 12, and 6. And this is a balanced reaction. Great. If you understand it all, then you're going to love this one, because this is a very challenging reaction to balance by inspection. But my thought is, if you can do this one, you can balance anything. So look at the process. It's going to be exactly the same as before, but it's just a little more challenging. This is a reaction of potassium superoxide, KO2, plus carbon dioxide and water to form potassium bicarbonate, which is essentially baking soda. Baking soda is sodium bicarbonate, plus O2. And this is a reaction in emergency oxygen supplies. So for instance, if your airplane gets damaged and the masks actually drop out of the ceiling, that oxygen supply is potassium superoxide. You exhale into the mask, you exhale carbon dioxide and water. It reacts with the potassium superoxide to make potassium bicarbonate and O2. You inhale the O2, and then when you exhale carbon dioxide and water. It reacts with the potassium superoxide, and the process repeats. And so you exhale these 2 things, and you inhale this thing. So let's balance this. Using the rule of putting a 1 in front of the most complicated compound or molecule, we'll put a 1 here. Using the rule of going to the beginning of the reaction next, we'll balance for potassium. We're going to leave O2 for last. Balance for potassium, that means we put a 1 here. Balance for carbon, there's only 1 carbon, so we need to put a 1 here. And balancing for hydrogen, again, we're leaving O2 for last. We have 1 hydrogen on this side, so whatever we put here multiplied by 2 has to be 1. And so that means we're going to put a 1/2 here. And now, to solve for what oxygen is, it's a little bit complicated, but the process is exactly what I did before, which is trying to figure out how many oxygen atoms we have on this side versus how many we have on this side. And for right now, let's put an x here and write an algebraic expression for what x is. We have, for the number of oxygen atoms on the left-hand side, 1 times 2, which is 2, plus 1 times 2, which is 2, plus 1/2 times 1, which is a half, and that is equal to 1 times 3 plus x times 2. Now this is no different from what I was doing before. It's just that we have so many terms, it made more sense to write it out longhand. And if you solve this equation, you get x is equal to 3/4. So in other words, this is 3/4. And now if we clear the fractions, we have to multiply through by 4 to clear this fraction. And so this balanced reaction will be written 4 potassium superoxides plus 4 carbon dioxides plus 2 waters goes to 4 potassium bicarbonates and 3 oxygens. Okay? Well, what have I done? I've shown you the method of balancing reactions by inspection. I've given you some hints on how to do it. Believe me, the only way to master this material is to just go out and practice a bunch of them. And finally, if you can solve this level of complexity, if you can solve a problem of this level of complexity, you're golden. You'll be able to solve it come test day.